Today we're going to talk about Magnons once again and spin waves, but now we're going to treat this problem from a purely quantum mechanical perspective. Remember, in our previous lecture we motivated the concept of spin waves and we treated the spins which are localized on the different atoms as vectors. So these are the different lattice sites. And the spin waves are treated as excitations from the ground state. So one possibility is that these spin vectors, they are deviated or they fluctuate from their ground state. And what is the ground state? The ground state is when the energy is minimized, the magnetic moments are parallel to the applied magnetic field. But that magnetic field could be an internal molecular field. But the spin waves are excitations from the ground state. They're excited states. And associated with these excitations, we defined the quasi-particles called Magnons, which are the magnetic analog of phonons. Now, phonons are quantized oscillations. Magnons are quantized spin configurations. So what we did, we wrote down the equations of motion for the spin at the nth location. We observed that this spin experiences a torque due to the spins in the neighboring locations. And then we proposed a trial solution for Sn. And with that trial solution, we came up with a dispersion relationship. And the dispersion relationship that we obtained was omega is, could you tell me what the dispersion relationship was? It's proportional to sine square Ka over 2. What's the proportionality constant? 4Js? 8Js. This is squared, or this is like this? This is like this. Is this omega square? This is omega is 8Js into this. So this is the dispersion relationship. And this was vividly different from the dispersion relationship for phonons. So if you plot the dispersion relationship, so this is omega, this is k, this is omega. For phonons, and we only plot the dispersion relationship up to, say, this is Ka, this is pi, this is minus pi. So this is the first Brillouin zone. For phonons, we have a dispersion relationship which goes as a sine. This is proportional to sine. Whereas for Magnons, the dispersion relationship goes as sine squared. So this is for Magnons, and this is for phonons. In the long wavelength regime, the dispersion relationship for Magnons varies as k squared, whereas the dispersion relationship for phonons varies as k. So you get different dispersion relationships. Now, Muzammil asked this question of what does this have to do with the boson operators, and these spins are actually fermions, though it's not necessary. These spins could be fermions or bosons. How do bosons come into the picture? And I'm treating the Magnons as bosons. So in order to answer that question, we would use the formalism of the second quantization to rederive in fact the dispersion relationship for the Magnons. So we're going to use a purely quantum mechanical approach. And this is the starting point for a discussion of how quantum field theory applies to condensed matter systems. Now, how do we start this discussion? We start this discussion in the following way. Suppose we have a collection of spins. Each spin is S. This could be half, 1, 3 by 2, etc. Now this spin has a certain projection along a quantization axis. Suppose the quantization axis is the z-axis. So that projection is Sz. And this Sz is characterized by the quantum number ms. So given an S, there are certain allowed values of Sz. Okay? So for an S, the allowed values of ms are S, S minus 1, S minus 2, all the way down to minus S. So there are two S plus 1 allowed values of ms. And now we have the spin operators. The spin operators are Sz, Sx, and Sy. And there is a certain commutation relationship between these operators, and that is S alpha commutator with S beta is some I, the Levi-Civita symbol, alpha, beta, gamma, S gamma. Where I'm taking, in today's lecture, I'm taking H bar to be equal to 1. Okay? So these are the commutation relationships for the spin operators. Now we've also noticed that if I make a plot, table between ms, S, ms and the number of Magnons, let's see what this happens. If ms equals S, then the projection of the spin is wholly and solely the angular momentum, which means that the spin is in its ground state and no Magnons are excited. So corresponding to an ms equal to S, the number of Magnons that are excited is 0. Now if ms decrements by 1, which means that the new value of ms is S minus 1, then this means that we are taking angular momentum away from the system. Corresponding to this decrement in ms, we're taking out a magnetic moment Gj mu b, which means a Magnon has been excited. So corresponding to this value of ms, there is one Magnon in the system. We have created a particle. It's just like having a two-level quantum system or a multi-level quantum system. If the electron makes a transition from n to n minus 1, a photon is created of a certain frequency. So now the angular momentum of the system, the z component has decremented by 1, it injects a Magnon into the system. I don't understand the question. If, what do you mean by excited state? It could all be populated, it could be still be in the ground state and there could be an electron at the nth level. This is the ground state configuration of the system, that there is an electron here. Whenever it makes a jump downward, a downward transition, it injects a photon into the cavity. Now whenever the angular momentum z component decrements by 1, a magnon has to be created. Okay? So if this is s minus 2, 2 magnons are created. If this is s minus n, n magnons will be created. Now its minimum value is minus s. So when this is minus s, 2n magnons will be created. So that's the maximum number of magnons that can be created from a single spin s particle. Okay. All of these are, of course, they have lower magnetic moments, but that creates magnons inside the system. So this means we can define an angular momentum operator Sz as S minus n, where n is the number operator. G. They are the ground state. So this means it comes here. So this means 2n magnons are created. But remember we're talking about a ferromagnet. For an anti-ferromagnet the situation will be different. We're talking about a ferromagnet exclusively here. So we can define an angular momentum operator Sz as s minus n, where n is the number of operator. Its eigenvalues gives the number of magnons inside the system. Likewise, we also know that we can always define the ladder operators. The ladder operators are Sx plus iota Sy minus, giving you minus sign here. So now these are our defining operators. The z component of the angular momentum is s, some operator. I can call this s into the identity. S is just a number minus n. Order. Now what we would like to do is we would like to transform from the spin operators to the boson operators, because magnons are bosons. So we would like to perform a transformation from the spin operators to the creation and annihilation operators. There are different kinds of transformations that have been proposed. One of them that I'm going to use is called the Holstein-Primakoff transformation from the 1940s. Now remember that our ladder operators have certain eigenvalues, and these ladder operators act on the ms states. For example, if I have ms, the s plus operator acts on this state as it increments the value of ms. So what this creates is ms plus 1 and a certain coefficient with this, and that coefficient is ss plus 1 minus ms plus 1 under root. This is the action of the ladder operator. This is what you learn in basic quantum mechanics. And if I have a minus sign here, then this decrements the value of ms, and this plus is replaced by minus. So this is the action of the ladder operator. And we also know that the sz operator, when acts on ms, this is an eigenstate of ms, this produces ms, an eigenvalue ms at the same state. Remember, I'm taking h bar to be equal to 1. There is an h bar here and an h bar here in absolute terms. Now if I have an angular momentum projection ms this corresponds to a certain number of Magnons. Now if I have a certain value of ms, the number of Magnons, I will have a certain number of Magnons. So what I could do is I could replace this label. This is just a label. This is a quantum state. I could label this as n, where n is the number of Magnons. And I will have a certain relationship between n and ms, these labels. So what I'm going to have is that the number of Magnons or bosons inside the system is s minus ms. If ms equals s, I have 0 Magnons. If ms equals minus s, I'll have 2n Magnons. So the relationship goes as this. If the s plus operator acts on ms, it increments ms, it lowers the number of bosons. And vice versa. If s minus acts on ms, it lowers ms and creates a boson. So now this is my relationship between the number of bosons s and ms. So let's look at, for example, S plus acting on ms. What I would like to do, I would like to see what happens when S plus acts on n, on the state n. So I have a system with n bosons and the ladder operator acts on the system. This S plus operator acts on the system. I know from this relationship, so what I could do, I can I can replace the ms by n's and see what this coefficient is going to turn out as. So what I'm going to do now is I'm going to take this coefficient here, s plus 1 minus ms plus 1, 1/2. This is s plus 1. Now my ms, this ms over here, this thing is s minus n. So I take this value of ms minus s minus n plus 1. Let me simplify this a little bit. So this is s square plus s minus s square minus sn plus s minus ns plus n squared minus n. What I could do, I could make some cancellations and s squared goes away. S n plus n minus n squared. This gives me n under root 2s plus 1 minus 1 . Now what does this mean? If I look at this relationship over here, I have the S plus operator acting on a state n. Right? This ms is now labeled as n, the number of bosons inside the system. When I have this S plus acting on n, I get this object here. And I increment ms, which means that I decrement n by 1. 2s plus 1 minus n. Now I will make one assumption here. The assumption that I'm going to make is that 1 over s is much smaller than 1, which means that my s is much larger than 1. What does this mean? This means that the fluctuations are small. So really the fluctuations in s, which are given by delta s, the fractional fluctuations are really small. So if I have this kind of relationship, I can use the Heisenberg's uncertainty principle. I have an uncertainty in I, in the ith component of the angular momentum, and an uncertainty in the jth component of the angular momentum, and I multiply these out. Now this uncertainty is lower bound by the commutator of Si and St, which is some Sk. Now if this uncertainty is smaller than the spin, then this means 1 over s is a large quantity, means the right hand side is going to be small, which means that this object is small, which really means that 1 over s is much smaller than 1, or s is much larger than 1. So this shows that the fluctuations are small. When the fluctuations are small, I can just ignore this 1 here. Okay, so now this thing becomes under root n 2s minus n minus 1. Oh, remember this is modulus squared. Now when I have this kind of relationship, I know that if I have n bosons inside the system, and from this I would like to decrement the number of bosons, this I could do using an annihilation operator. So I already know certain relationships for the creation and the annihilation operator. So if I have n bosons in the system, then I could apply the creation, the annihilation operator on this state. This decrements the value of n by 1, and there is a certain coefficient that goes with it.
Sn plus 1, S hat plus n minus 1,
ये वाला यहाँ पे n plus 1 No, what's going to happen is that this s plus this is a spin operator. This spin operator is acting on ms, it's incrementing the value of ms. But when the value of ms is incremented, you go up this table, the number of bosons goes down. So incrementing the value of ms is annihilating a magnon. N is the label for the number of magnons. The number of magnons is actually going down. Okay? It's just in accordance with the table and the discussion that we had over there. So now what we're doing is we're decrementing the number of, annihilating the bosons, and the corresponding annihilation operator is given by this. The corresponding creation operator is defined in this fashion. Alright? So now if I look here and I look here, I can replace this state with, all of these are numbers. I can replace this thing with V, the annihilation operator, divided by under root n, acting on kek n. This is what happens when S plus operator, which is a spin operator, acts on a Magnon state. So this is a defining relationship, and it's a defining moment in our discussion too, because now we are able to define a transformation which is the Holstein-Primakoff transformation, which relates the spin operator to the creation and annihilation operators. And this is now evident that this under root n goes away, and I'm left with 2s minus n 1/2. Now this n could also be replaced by creation, and this is also an operator here. This is really, okay, let's call this A. Creation and annihilation operators, A. This is A dagger A. This is one transformation. The transformation relates the spin operator to the corresponding annihilation operator. The other transformations can be written in a straightforward fashion. So S minus, which is the conjugate of S plus, is just going to be the conjugate of this thing. The conjugate of this is A dagger 2s minus A dagger A. This is Hermitian, remember, 1/2. And SZ, we've already noticed, equals S minus N. N is A dagger A. So now we have explicit transformations between the spin operators and the creation and annihilation operators. And what we expect is that we would like to express the Hamiltonian, which is based upon the exchange interaction for a ferromagnet, and we would like to see whether it corresponds to the Hamiltonian for a harmonic oscillator. And from that we would like to derive the dispersion relationship. So now these are the Holstein-Primakoff transformations, which convert from the spin operators to the bosonic operators. Okay? And they can also be written in this fashion. S plus is under root 2s 1 minus A dagger A over 2s 1/2 A, and S minus is under root 2s, which is just a number, A dagger 1 minus A dagger A over 2s. And the third one is SZ minus is equal to S minus A dagger A. S really means a number with the identity operator. So these are the transformations. Remember, observe a 1 over S appearing here. So when we expand this square root, we'll use the binomial expansion, we'll take the assumption that 1 over S is large, which means that this thing is really small. So in order for this transformation to work, we'll have to work under the assumption that S is much larger than 1. Or the number of Magnons that are excited is smaller than S. The fluctuations are small. Okay, so you're in the low energy limit, which is really the quantum limit. Alright, so now we have these transformations. Now let's move on to the Hamiltonian for the system. Okay, is there any question up to this point? So remember that we're looking at the second quantization formalism here. Now let's write the Hamiltonian for a ferromagnet whose ferromagnetism derives from the exchange interaction, the Heisenberg exchange interaction. The Hamiltonian for such a ferromagnet is something we've seen ample number of times, given by H. J is minus 2 Jij Si dotted Sj sum over I less than j. That is sum over all i's and j's where I is not the same as j. Now first of all, let's do this problem in parts. Let's just look at two spins first. So if you look at two spins, I have S1 dotted with S2. Now this is of course S1z, S2z plus S1x, S2x plus S1y, S2y. This is the exchange interaction. Now this is straightforward. If I look, now what I would like to do, I would like to express the Hamiltonian in terms of the bosonic operators. So, and I have the transformations that are now available. Okay. So this object here, I can write this as S minus N1 number operator for the first spin into S minus N2. I assume that all the spins have the same S. So this is S square minus S N1 operator plus N2 plus N1 operator, N2 operator. Okay, so this term is clear. This is equal to this. Now let's look at this term over here. In order to do that, we would first like to express the x and the y in terms of the ladder operators, because we have the transformation from the ladder operators. Is everything some clear picture?
Yes.
Alright. So now we would like to express this component. This is called the planar part of the Hamiltonian because it's in a plane. This is called the icing part of the Hamiltonian. This thing. Now if you look at the planar Hamiltonian, I would like to express the x's and the y's in terms of the ladder operators which are given over here. So now what we would like to do is we would like to look at this expression over here. If you look at this expression, Sx is going to be given by S plus S minus over 2. And Sy is written as S plus minus S minus over 2 iota. So this is a transformation. So now I would like to replace these values of Sx and Sy in here, so that I can express the planar Hamiltonian in terms of the creation operator and in terms of the ladder operators. Now when I do that, when I make this transformation, this thing over here becomes 1/2 of S1 plus S2 minus plus S1 minus S2 plus. When I insert these values of Sx and Sy, I get this result over here. Now I have the Holstein-Primakoff transformations. What I could do now is I could replace the S pluses and the S minuses with these expressions which involve the creation and annihilation operators. Let's do that. So 1/2 S1 plus S2 minus plus S1 minus S2 plus. Sometimes this kind of Hamiltonian, in which there is a rising operator on one term and the lowering operator on the other, and then you swap the roles, it's called a flip-flop operator. Okay, flip-flop. Now if you look here, this is 1/2. Now let's see what S1 plus is. S1 plus is, so under root 2S is common all the time, and I have 2 times this. So this is 2S. Now S plus is 1 minus N1 over 2s 1/2 into A1. This is this thing here. Now this thing is 1 minus n2 over 2s. There's an A2 dagger here. Plus A1 dagger 1 minus n1 over 2s 1/2 1 minus n2 dagger over 2n2 A2. Now what I could do, I could expand this as powers of 1 over s. I could expand this as powers of 1 over s. I could expand this as powers of 1 over s. And if I assume that my s is large, which means that this term is small, then I could use the lowest order. I could retain the lowest order term. So if I retain the lowest order term, this half is replaced by a 4 here. Okay? So I get 4 here. It's just a binomial expansion. And now I could do an explicit, I can open up these brackets, I can expand this in the following fashion. This is S into one minus n1 over 4s a1 a2 dagger minus a1 a2 dagger. Now this n2 is a2 dagger a2 over 4s. This is algebra here, plus a1 dagger 1 minus a1 dagger a1 over 4s a2 minus a2 dagger a2 over 4s. This is S a1 a2 dagger minus a1 a2 dagger a2 dagger a2 4s minus a1 dagger a1 a1 a2 dagger 4s plus a1 dagger a1 a1 a2 dagger a2 dagger a2 4s plus a2 a1 dagger minus a1 dagger a2 dagger a2 4s. This is 16s squared over here. Minus a1 dagger a1 dagger a1 a2 4s plus a1 dagger a1 dagger a1 a2 dagger a2 4s, and of course there will be higher order terms as well because we've already truncated the c's. Now what we would like to do is to make an assumption here. We truncate this series and we only preserve the operators that are quadratic. So we preserve this and we preserve this. Okay, so the lowest order terms we preserve. So we ignore this, ignore this, ignore this, this, this and this. So this part of the Hamiltonian becomes S A1 A2 dagger plus A1 dagger A2. So now for two spins, the Hamiltonian, for spins 1 and 2, alright, the Hamiltonian is minus 2 J 1 2, the interaction between the two spins, S squared minus S N1 plus N2 plus N1, N2 plus S A1, A2 dagger plus A1 dagger A2. This kind of Hamiltonian is called a Hubbard Hamiltonian or a tight binding Hamiltonian. A tight binding Hamiltonian. Intuitively, what this means is that at site 1, you are applying an annihilation operator, and at site 2 you are applying creation operator. So this means that in terms of hopping, if you look at this in terms of hopping, an electron say is moving from one site to another. It's created at one site and it hops on to another site. Or a magnon is being annihilated here and being created on a neighboring site. So one spin goes down here and it goes up here. So a magnon is created here and annihilated here, or a magnon is annihilated here and created here. Okay, so it represents the hopping of magnons in a sense. A magnon is created on one side and is annihilated at the other side. Okay, so the same kind of Hamiltonian describes hopping conductivity in graphene. So this is our Hamiltonian for two spins. Now what would we like to do? Now let's write down the Hamiltonian for all the spins, for the entire system. That Hamiltonian H, J is, and we suppose that all the J's are the same and there are only nearest neighbor interactions. Only nearest neighbor interactions. And all the J's are the same. So I add minus 2J. Now this is S squared. Remember that this is the Hamiltonian for each pair. If I draw a single chain, H12 is the Hamiltonian for a single pair. And there are many such pairs inside. the chain. Okay? How many pairs exist? N by 2. So the first term is how many pairs exist? N over 2 into S squared. Plus 2js. Now these are two spins in a pair, this spin and this spin in a pair, and I have to do this for all pairs. So what I could write this as 2 times sum over all the spins. I put in a 2 here to take into account both spins in a pair, and I replace each one of these operators by am dagger am, which is a number operator on each spin, and I put a 2 here to take into account both the spins inside the pair, and I sum up over all the spins inside the lattice. Okay? Now I have to take into account this term over here. Now if I write this as minus 2j, I have, now these are neighboring spins. So I have nm, number operator on the n spin, number operator on the m plus 1 spin, and I sum up over all n's, over all the spins inside the solid. Okay? Then I have this thing here. This is minus 2js and I have a on the m spin, a m plus 1, I have the creation operator plus a m creation operator, a m plus 1 annihilation operator. So this is my Hamiltonian graph. Half a minute of reflection and then we move on from here. There is an S here as well, to the S. Right? Now, interesting. This is just a constant, right? This thing is just a constant. Depends on the size of the system, it depends on S, it's just a constant. This thing over here is of 4th order integration and annihilation operators. This is am dagger am plus 1 dagger am plus 1. So this is 4th order. So on the same footing, we can actually ignore this. This term, if you look at it from a physical perspective, represents a Coulombic interaction. Because this is, it's like a Coulombic interaction because this is the population of, on the mth side, this is the population on the m plus 1 side. So now basically I'm left with this term and I'm left with this term. So my simplified Hamiltonian becomes 4js sum over all the spins of the number operators minus 2js sum over all spins of this tight binding Hamiltonian am plus 1 dagger plus am dagger am plus 1. Okay, this is the Hamiltonian that I need to work with. So it's nice to diagonalize this Hamiltonian so that I can find its eigenvalues. The eigenvalues of this Hamiltonian will give me the dispersion relationship. Okay, so now how do I diagonalize this? I diagonalize this Hamiltonian by Fourier transformation. Now how do I do that? I define the Fourier transform of the creation and annihilation operators. If I have the creation of the annihilation operator an or aj, I can define this Fourier transform in the following fashion: aj minus I q rj sum over all j's. This is the definition of Fourier transform with an appropriate normalization constant 1 over under root n. This equals the Fourier transform of A, which I call B, and this is indexed by Q. Q is the variable that is conjugate to R. Remember, R is a position variable and its conjugate variable is a wave number K or Q. So this is the definition of the Fourier transform, and if I take the complex conjugate of this expression, I can find B2 dagger. B2 dagger is 1 over under root n j a j dagger e plus iq rj. So this is our definition for the Fourier transforms. Now what we have here are the creation and the annihilation operators. So we would like to express the creation and annihilation operators in terms of these, which means we would like to compute the inverse Fourier transforms of these. Okay, so how do we do that? That's simple. Aj equals 1 over under root n sum over all the modes, all the wave numbers q of bj e plus I q rj. Right? bq. If I take the inverse, the Hermitian conjugate of this, aj dagger is 1 over under root n sum over all the q's bq dagger e minus I q rj. So these are our definitions for the Fourier and inverse Fourier transforms. Now we would like to take this Hamiltonian and insert these values of a's in here. So we would like to express this Hamiltonian in the Fourier domain. Sometimes easier to look at this in the Fourier domain. Probably it gets diagonalized in the Fourier domain. That's what we would like to investigate. However, there's one small exercise that needs to be done before we actually delve into this, and that's a very simple exercise, which is the following. I know that the commutator between ai and aj dagger is the Kronecker delta ij. right? This is the commutation relationship. Now what I need to do, I need to find out the commutator between BI, BQ and BQ prime dagger, right? And we would like to verify whether these are really creation and annihilation operators. A creation and annihilation operator should be a bosonic operator in the Fourier domain as well. So I would like to verify this. So now I can simply take the expressions for the BQs. This is sigma j 1 over under root n, 1 over under root n, 1 over n, sigma j, aj, e minus I q or j, right? Sigma I a I dagger e plus I q r I. All right. This is Q. I would just like to find this thing out. All right. Now this is a sum. This is a sum. Now we know that AJ, the commutator of AI and AJ dagger is non-zero only when this index is the same as this index. Correct? So when these indices are same, I'm just sampling one value here and I'm sampling the same value of j from here. Which means that I really have 1 over m j aj commutator a j dagger. I have this thing over here. And then I have these coefficients which are I q dotted with r I minus r j is the same as I. So I put an I here or I put a j here and I put a j here. This is 1. Now this gives me 1 and I have n of these, so I get 1 as the answer. N over n is 1. So I have proven that the Fourier transform creation and annihilation operators also obey the appropriate commutation relationship for the bosonic operators. Now what we would like to do, we would like to look at our Hamiltonian over there. And we would like to insert the Fourier coefficients in there. So there are 3 kinds of terms that we encounter. One is this term, one is this term, and one is this term. So let's look at these 3 kinds of terms independently. I have one term which is am dagger am. Okay, this is my first term over here, first kind of term. Now I would like to express this in terms of the Fourier components. This is going to be equal to 1 over n. The dagger is given at the bottom, q, bq, dagger, E minus q. Now what is Rj here? Since I'm talking about m, so Rj is really m into the lattice translation vector A. Right? If I were Aj here, this would be Rj. If I have Am here, this is Rm. Now the position of the mth side is m, it's an index into the lattice translation vector A. Okay, so I have this thing and I have AM. AM is, I can put a Q here. Now AM is BQ E plus IQ M A. This is AM rate. Remember this, I can label this as Q prime, doesn't matter. This is actually Q prime because I have to take a sum here and I have to take a sum here. Now if I perform this multiplication, I get terms of the kind Q minus Q prime. I get terms of the kind, right? If I perform this multiplication, I get terms of the kind Q minus Q prime, which is a wave vector. Now I'm taking the sum over all the Q's. Now if you have a large system, the average of an oscillatory function, which is Q minus Q prime, is going to be 0. So I only preserve those Q's which are common in both of these. So when I perform this multiplication, I get 1 over n Q, only Q, BQ prime, BQ dagger, BQ. This Q prime is sampled and it only samples out to be non-zero where Q prime equals Q, because otherwise the exponential terms will average over the entire system to be 0, because you have many modes inside the system, many values of Q. Okay, so I get BQ dagger BQ, and from here I get this thing multiplied with this thing gives me 1. So I get this term over here. So now I found AM dagger AM equals this. Now let's find the second term. The second term is AM into AM plus 1 dagger. All going to turn out really nice. AM into AM plus 1 dagger. This is the second term. Now if you look over here, this is going to be equal to 1 over m. This thing is the same as this, Q, BQ dagger E minus IQ plotted with MA. AM plus 1 is now once again a sum over all the Q primes, Q prime, B, Q prime, A plus I, Q prime, M, A, E plus I, Q prime, A. Right? I've just written M plus 1 into A as M into this. Once again using the same argument, that is, I would only like to preserve the Q primes which are the same as Q, because otherwise averaging will give me 0. I'm left with 1 over n sum over all Q's, all modes, which is BQ dagger BQ, and now I'm left with this term over here, which is E I Q A. Let's write, suppose it's a one-dimensional system, Q is in the same direction as the lattice vector. I'm left with E I Q A. This is this second kind of term that appears in the Hamiltonian. Now let's look at the third term, which is AM dagger into AM plus 1. See, this is a purely quantum mechanical, this kind of treatment is called the second quantization. So I have AM dagger AM plus 1. This becomes 1 over n. AM dagger is Q, B, Q, dagger. Okay, so if I have this term over here, am dagger into am plus 1. Now we do know that am into am plus 1 dagger is going to be 0 because these are operating on different spins. So what I could do, I could reverse the order here. Let me see if I'm am dagger, am plus 1, am plus 1 dagger, am. So I have am plus 1. I can write this as a. So since this is 0, I can reverse the order. It doesn't matter. So this becomes am plus 1 into am dagger. Right? There's no harm in doing that because these operators act on different sides. They commute. Correct? This is an annihilation operator on the m spin. This is a creation operator at the location of the m plus 1 spin. So I can reverse the order. So when I reverse this order, this third term over here, this term can also be written as am plus 1 into am dagger. Correct? नहीं समझे? Really? This is fine. So what I'm just looking at the third term and I'm swapping the order of these operators so that I am in consistency with this kind of expression in which the first spin is without a dagger, the second operator is with a dagger. So I'm making the third term consistent with this. Okay, just it's a mathematical trick. I'm reversing the order of the two operators in the third term over there. I can do that because these operators act on different sides, they commute. So when I look at this, this thing becomes 1 over m. am plus 1 is bq dagger e minus I q m a e minus I q dot a. This is am plus 1. My am dagger is q prime bq prime e plus I q m a. Okay. Now once again I'm left with, I do the sampling q, bq dagger, bq. Now I'm left with e minus iqa. So now I have all the three terms inside the Hamiltonian expressed in terms of the Fourier transform operators. Now I can write down the Hamiltonian. The Hamiltonian for the entire spin, which is the exchange Hamiltonian, is given by 4js into am dagger am squared, which is this thing over here. Correct? This is 1 over m bq dagger bq minus 2js m q 1 over n b q dagger bq e iqa plus e minus iqa. Now since there are n is the total number of spins, the summation over m will make this n go away, right? And I'm left with sum over q's. Okay. Summing over m's, 1 over n times gives me n times 1 times n, which is 1. Now, if I look here, this is 4js sum over q bq dagger bq one. Now, what is this? This is 1 minus cosine of QA. Extremely nice. This is 8js sum over q sine square QA over 2 BQ bracket BQ. And doesn't this give me, this is the Hamiltonian for a harmonic oscillator. Okay, exactly the Hamiltonian for a harmonic oscillator. So the Magnons behave just like a harmonic oscillator, and the energy of the Magnon is this term over here. The energy of the Magnon is h bar omega. This must be equal to h bar omega. If I forget the h bar for the time being, omega is 8js sine square. Previously I used k, so I can use k once again. This is the same result that I obtained using the semi-classical approach, and the second quantization reproduces exactly the same result. So I would like to stop here. So you could do an exactly similar calculation for an antiferromagnet and derive the dispersion relationship for an antiferromagnet. It's slightly more complicated because additional transformations are required. But nevertheless, the basic essence of using the second quantization to derive the existence or motivate the existence of Magnons is universal. Okay, and this automatically gives us a dispersion relationship. So in our next lecture, we're going to look at some more ferromagnetic phenomena. We're going to look at the Stoner model and see how the Stoner model is straddled in between the mean field model and the spin wave model. Inshallah, see you on Thursday. I've uploaded a new homework by the way. Thanks.